Let me take you inside the lab. This is exactly how Steve Lamoureux measured the Casimir effect in 1996. The year is 1996. Steve Lamoureux is at the University of Washington. He wants to measure a force from nothing. But first, he needs to build the experiment. Every detail matters. Step 1. The Platz Lamoureux used 2 plates. One was flat. The other was a polished sphere. The flat plate was made of chromium. It was 5 millimeters wide, 5 millimeters long, and 0.3 millimeters thick. That's thinner than a credit card. The sphere was a lens, a polished optical lens. It had a radius of curvature of 50 centimeters. That's half a meter. It was coated in gold. The coating was 0.1 micrometers thick. That's 100 nanometers, about 1,000 atoms thick. Why a sphere instead of 2 flat plates? Because you can't get 2 flat plates perfectly parallel. They'd tilt. They'd touch at one edge. But a sphere and a flat plate have a well-defined distance at every point. The sphere sits above the flat plate. The closest point is measured. Everything else is farther away. It's mathematically clean. Step 2. The distance, the gap between the sphere and the plate, was between 0.5 and 6 micrometers. That's 500 nanometers to 6,000 nanometers. For reference, a human hair is 100 micrometers thick. These plates were closer than a hair. Much closer. How did they control that distance? Piezoelectric crystals. A piezoelectric crystal expands or contracts when you apply a voltage. Lamoureux used one to move the sphere. He could control the distance to within 10 nanometers. That's 10 billionths of a meter, less than the width of a single atom. The Apratust apparatus was a torsion pendulum. A thin wire held the flat plate. The wire was tungsten. It was 100 micrometers in diameter. That's 0.1 millimeters. The wire was 50 centimeters long. The flat plate hung from the wire like a swing. The sphere was mounted on a separate platform. A piezoelectric tube moved it. The whole thing was inside a vacuum chamber. The chamber was pumped down to 10^6 torr. That's 1 billionth of atmospheric pressure. Almost a perfect vacuum. Why a vacuum? Because air molecules would hit the plates. They'd create a force. That would mask the Casimir force. So they removed all the air. Step 4. The weighted flat plate weighed 0.3 grams. The sphere was mounted on its platform. The total moving mass was about 1 gram. The torsion pendulum was incredibly sensitive. It could measure forces as small as 1014 newtons. That's 0.000000000001 newtons. For reference, the weight of a single bacterium is about 1012 newtons. This was 100 times smaller than a bacterium. Step 5. The problems. Problem 1. Vibrations. The ground vibrates constantly. People walking, trucks outside, even the building swaying. If the pendulum moves from vibration, you can't measure the Casimir force. The solution: a heavy granite block. The granite block weighed 1,000 kilograms. That's 1 metric ton. It was placed on 4 pneumatic legs. Air was pumped into the legs. The granite floated. It isolated the experiment from ground vibrations. Problem 2. Static electricity. The plates are metal. They have charges. If they attract or repel from static, it masks the Casimir force. The solution: gold coating. Gold doesn't oxidize. It doesn't build static charge, and they grounded everything. No charges, no interference. They also passed an electrical current through the plates. This measured the contact potential. They corrected for it in the calculation. Problem 3. Temperature. Heat makes materials expand. A tiny temperature change changes the distance between plates. Even 0.1 degree matters. The solution: the lab was kept at 20 degrees Celsius, constant. They also used a thermometer to measure the temperature. They corrected for thermal drift. The temperature stability was 0.01 degrees per hour. Problem 4. Alignment. The sphere had to be perfectly aligned with the flat plate. If it was off by even 1 micrometer, the measurement was wrong. The solution: optical alignment. They used a microscope to position the sphere. They could see the gap. They adjusted it until it was perfect. The alignment accuracy was 1 micrometer. Step 6. How do you measure the twist? A laser. A laser beam bounced off a mirror attached to the pendulum. The mirror was gold-coated. It was 2 millimeters in diameter. The laser was a helium neon laser. Wavelength of 633 nanometers. It was focused to a spot size of 0.1 millimeters. The reflected beam hit a position-sensitive detector. When the pendulum twisted, the mirror moved. The detector measured the movement. It was sensitive to displacements of 0.1 nanometers. That's 1/1000th of a meter. They measured the force at 20 different distances. They took 100 readings at each distance. Each reading took 10 seconds. Total measurement time, 20,000 seconds. That's 5.5 hours. But the experiment took months. They had to repeat it. They had to test for errors. They had to validate everything. Step 7. The resource measured force was 5 piconewtons at 1 micrometer distance. That's 1.5 times 10^12 newtons. For reference, the weight of a single red blood cell is about 50 piconewtons. This force was 30 times smaller than a red blood cell. When they plotted the force versus distance, it matched the Casimir theory perfectly. The force dropped off as distance to the 4th power, exactly as predicted. The measurements were accurate to within 5% of the theoretical value. Lamoureux had done it. He had measured the force from nothing. Empty space was not empty. The quantum vacuum was real, and it had physical effects. Step 8. The legacy today, we have much better experiments. Atomic force microscopes can measure the Casimir force with 1% accuracy. But Lamoureux's experiment was the first definitive measurement. It proved the theory. It opened a new field of physics. The Casimir effect is now used in nanotechnology. It's studied in condensed matter physics. It's even considered in gravitational wave detectors. It's a fundamental part of quantum physics. This is how you measure the impossible, one careful step at a time.